to settle down here. We're going to settle down here. Thank you. All right. Welcome to you. Welcome to United Astronomy Clubs of New Jersey. We're back here live on site. Just so you know, we are live streaming this. So if you ever can't come see us here on site, you can always check us out online on YouTube. We have all our past broadcasts kept there. And you can always come join us live. Right. So to get started, a couple things for our online audience. Do check us out on our website, uacnj.org. That is where you can find a list of all our programs that we have set for this season and any special events that we may do, plus information about our member clubs. In addition, we have our socials, Facebook, Instagram, Twitter, Discord. You can check us out there. And as always, we are a nonprofit, so all your donations have helped go to keeping our lights on and allows us to keep offering that free public outreach. Now, for those of you who are here, there will be a question and answer session at the end. If you need to use the bathroom, we have the porta potty to my right, your left. We do also have a little gift shop and museum area, and I'll be in there after the question and answer session, should you want. Right. When we go to leave, we're going to use our headlights because we do like staying safe and not running people over. Trust me, it hurts when you get run over. We're not going to ask why I know that. Right. However, if we have any flashlights or whatnot, we're going to keep the light pointed towards the ground. It just prevents any unnecessary blinding because as much as we need the headlights for safety, we don't want to unnecessarily just have people blinding us. Also, we are in a state park, so trash is carry in, carry out. So please just be mindful that we are picking up after ourselves. All right, with that, we're going to get into tonight's presentation with Paul. Paul's our current president here at UACNJ, and he's been doing astronomy for
almost 10 years.
A decent amount of time, and he's here to tell us about something that goes bang, whoosh, and zoom.
Bang, whoosh, and zoom. Exactly.
All right, with that, I'm going to let Paul give himself a little bit better of an introduction because I lost his little bio, unfortunately.
Just a war story. The way I started astronomy is I happened to be out late one night outside on the roof. I have a flat roof on a section of my house, and I looked up in the sky and I saw a bright object, and I said to myself, I think that's Jupiter. I had a feeling. I didn't know at the time. And took the binoculars and I laid down on the roof and I looked up at the sky, and through the binoculars I could see the Galilean moons. So binoculars only, not even a telescope, and I could see the moons of a planet. And that got me instantly intrigued because it was so not easy, but so approachable. I didn't know anything, yet I had already seen the Galilean moons. So I thought, wow, that's really cool. Maybe I should do more of that. So I purchased some reading material, a telescope, and here we are now, a amateur astronomer for almost 10 years. Excuse me while I switch presentations. All right, so here's tonight's presentation, Bang, Whoosh, Zoom. And this is a story of the Big Bang Theory. And I'll explain at the last slide why I called it Bang, Whoosh, Zoom. But also, besides just presenting the Big Bang Theory, This is more of a book report on a book I read called The First 3 Minutes. And the first 3 minutes was written by a gentleman named Steven Weinberg. The full title of the book is The First 3 Minutes, a modern view of the origin of the universe. It's the updated edition, and it was originally printed in 1977, and the update happened in 1993. So there was some older thinking about, and not old thinking, but some outdated information. He updated some of that information in 1993, but 1993 is already a little bit while ago, so the last slide will show some the most modern thinking on where we are in Big Bang Theory. So for any of that correct information, I credit completely Steven Weinberg, and he's actually, we will get into who Steven Weinberg was, but he gets all that credit, and any mistakes that you detect in my presentation, those all belong solely to me. All right, what are we going to cover when we talk about the Big Bang today? As I said, we're going to talk a little bit about the author, a quick review of some of the concepts that we need to know to understand the Big Bang. We're going to talk about the expansion of the universe and redshift. We're going to talk about the cosmic microwave background. We'll call it the CMB. And a few select moments in time. Steven Weinberg used that device in his book, and I think it brings the idea of what was happening, why things fit together so well in the theory. That device really worked in the book, and so I'm going to use it here tonight. And then finally, some afterthoughts on maybe some of the meanings, but also some of the questions still about the Big Bang Theory. So a little bit about Steven Weinberg. He was born in 1993, and he left us recently. He left us last year. And there he is in 2 photos here. And I wanted to, of course, I call this chalkboard scribbles and royalty. And anytime you see a photo of a physicist, right, he has to have funny symbols behind him on a chalkboard, right? That's just part of the mystique of being a physicist. Here he is. Steven Weinberg was a Nobel laureate. Here he is with fellow Nobel laureates meeting Queen Beatrix of the Netherlands. At that time, she was the queen. She's still with us, but she's no longer queen. She is now Her Royal Highness, her son. She abdicated to her son, and her son is now the king. A very abbreviated list of Steven Weinberg's professional achievements, and when I say abbreviated, multiple pages long of the things this gentleman has accomplished. He was very well respected and one of the great minds maybe ever to walk the planet. So here is his bio. He got his bachelor's from Cornell University in '54 and his doctorate in physics from Princeton in '57. He did original research and theories in particle physics and physical cosmology. And that sentence doesn't encapsulate what he accomplished. He is part of the reason that we have the standard model for particle physics today. So a major, major contributor. He shared the Nobel Prize in Physics with Sheldon Glashow and Abdus Salam in 1979. They both came up with the same theory. Weinberg independently of the other two, and it had to do with the separation of the weak force from the electromagnetic force in the early universe. He has numerous other awards in the sciences and for science advocacy. He was a researcher, various positions, but in various institutions, but he was a researcher or a faculty member or lecturer at Columbia, Berkeley, MIT, Harvard, and Texas at Austin. You'll recognize a lot of those university names, I'm sure. He had 15 books on science or science communication and science philosophy, and he has many credits for multiple scholarly and popular articles. So an accomplished person. So if he wrote a book on the Big Bang, I think maybe you can say that's a book you should read about the Big Bang. All right, so yay, science. Let's review some of these science concepts. And there are almost no equations. Almost is a different color, italicized, bolded, and underlined. So almost is an important word there. 100% guaranteed that there's almost no equations, or your money back. All right, we're going to talk a little bit about particles. We have here an image of a particle collision and the various particles created from that collision, and a particle accelerator itself. Particles that move fast enough when they collide will overcome nuclear forces and are annihilated. So a lot of people think that, or you might be tempted to think that particles smash together and then scientists count the pieces. That's not what's actually happening. Once those particles are annihilated, new particles are then created from the resulting energy. So no particle, energy's floating around, and then new particles just pop out of that energy. These particles generated are governed by their rest energy, whether they are created or not. So there must be enough energy around in order for the particles to be created. That energy is the rest energy. Particles are created in matter-antimatter pairs. The photon is a particle. It has zero mass, and it mediates the electromagnetic force, that is light. So photon is associated with light, and it is, in this case, a particle. Electrons are leptons and are small and have small mass. Protons and neutrons are baryons, and they are made up of quarks. They are larger and more massive than electrons. And neutrinos are also leptons, but they react very infrequently with baryonic matter. So infrequently that you could put a whole bunch of lead between us and a distant star, and you still would not have a lot of interactions with neutrinos through that lead. So we're going to talk about light. And over here we have the Young's double slit experiment and the resulting pattern over here. And in this case, we are going to talk about light as a different phenomenon. We're going to talk about it as a wave. Over here we have some spectra, and we're going to talk about redshift, and I will advance the slide to talk about them. We'll be coming back to that particular slide. Light can behave both like particles, as we said when we introduced particle physics, but also as a wave. Light from objects in space can be collected and analyzed. Their spectra and apparent luminosities can be directly measured. So we see those things, we can not feel them as much as gather actual data directly from those phenomena. Similar to sound waves, light is subject to the Doppler effect from relative motion. And if you remember, you might have seen in school, or you might notice it from any passing car or something like that, you get the classic round sound as a car passes you. That is the Doppler effect in sound. Doppler effect also applies to light. Redshifted light is lower frequency, longer wavelength from objects moving away from the observer and is less energetic. Blue shifted light is higher frequency, shorter wavelength from objects moving towards the observer and is more energetic. And let's go back to this screen here. So this is a compound on these absorption lines that someone identified maybe in a laboratory. So a compound, they shined bright light through a compound and saw these black lines, and they've identified those black lines to equal that compound, and it's that the same place anywhere that compound is in the universe. You shine light through it, you're going to get those lines. However, if that object is moving away from you, you get this red-shifted spectrum. So it's the same lines you can see, but they call it shift. And they call it shift is because what happened to these lines? Who can see up front there? What happened to those lines? Shift is a big clue. All right, I'll answer for you. They shifted to the right, towards the red. And same lines over here on a blue shifted spectrum. They shifted to the left towards the blue, okay? And that's what they mean by red shift and blue shift, is you get this phenomenon of the absorption lines moving one direction or another on the spectrum. Let's see, did I finish that slide? No. Visible light is a small piece of the electromagnetic spectrum from gamma rays to radio waves. So light isn't just light. Light is radio, UV, IR, gamma rays. All those things are electromagnetic waves or light. The fastest anything in the universe, including light, can travel through space, and through again is underlined a different color, bold and italic, can travel through space in a vacuum, is C, which is equal to 299,792,458 meters per second, or approximately 671 million miles per hour. So pretty fast. But it's an absolute speed limit. Okay, expansion and redshift. Let's talk a little bit about now getting into the book. Chapter 2 in the book, The Expansion of the Universe. Let's get into some of the history of how the Big Bang Theory came about. What are these things? Someone said it. Say it louder. Galaxies. 100% true. Those are galaxies. We didn't always know what galaxies were. In 1750, Thomas Wright proposed that the Milky Way was a flat slab of stars in which our solar system resides. And if you remember, at one point we thought the Earth was the center of the universe and everything else surrounding the planets and the stars were just revolving around the Earth. Well, piece by piece, we came to the realization that the universe was filled with maybe something else besides what immediately surrounded us. And part of that realization was that these other we existed in a system of stars, and that cloudy Milky Way we see in the sky every night was that system of stars. In 1775, Immanuel Kant proposed that some of the nebulae that astronomers observe are actually circular disks like the Milky Way. So we started getting the idea that maybe other galaxies besides the Milky Way exist. Though this idea was widely accepted, Kant's ideas of a universe full of galaxies was debated for the next 150 years. And the reason why it was such a topic of debate is that nobody could wrap their mind around the immense distances that would be required for there to be multiple galaxies in the universe. So it was a debated topic. In 1923, Edwin Hubble, you might have heard of Hubble, the name Hubble. Well, this is one of his major accomplishments. Observed Cepheid variable stars in the galaxy Andromeda, and using previous work from Henrietta Swan Leavitt and Harlow Shapley, proved that Andromeda, the galaxy, no longer considered a nebula, was its own separate galaxy and not a nebula in the Milky Way. Hubble's original estimate, approximately 1 million light years away, blew everyone's mind. But the modern estimate of how distant Andromeda is approximately 2 million light years away. So what does Hubble's discovery that galaxies existed mean? Well, astronomers weren't sitting around waiting for galaxies to be discovered and proven that they are their own separate thing. Since the mid-19th century, and among many other things, astronomers had been measuring spectral shifts, the redshift of light, of astronomical objects, including the previously suspected, now confirmed galaxies. It was quickly noticed that with only a few exceptions, all galaxies were redshifted. And what does redshifted mean again? We went over it a little bit. Redshifted means that things are moving away. So that's a pretty significant finding. Hubble announced in 1929 that he discovered that the redshifts of the galaxies in all observed directions increase roughly in proportion to the distance from us. That has significant implications. This became known as Hubble's law, accepted current thought on the value of Hubble's constant, at least the measured values. I think the accepted thought is actually a tighter range, but the recent measured values on Hubble's constant is between 67 and 77 kilometers per second per megaparsec. And this is actually Hubble's plot of his original findings. So you can see that's a nice straight line, which in math and in physics classes you can remember we were really happy when things were a straight line and not a curve, right? So what are the implications? Like I said, some of those things had pretty significant implications. So what are the implications of those findings? Well, first of all, things were moving. The competing theory of the universe at that time was that the universe is steady state. It's static. We found out that everything is currently expanding. Also, the universe is homogeneous and isotropic. So the fact that he found that everything, in no matter what direction he looked, was all moving away from us, meant that no matter where you are in the universe, it's all expanding. So if you were to go to one of the distant galaxies that you observed, all the galaxies from there are moving away from it. So anywhere you were, because everywhere you looked, the only way that you can accomplish that all galaxies are moving away from you, only dependent upon how far away they are, their redshift, meant that it's happening equally everywhere. This is known as the cosmological principle. We can now, furthermore, now that we know that it's not static and that we have this relationship, we can now play with the universe's time coordinate. If you think about it, if it was static and you move the slider on earlier in time or later in time, you couldn't tell much because the universe is static. But now that we know that the universe is expanding, we can play with that time coordinate and in our minds and fast forward to predict its fate. Not only can we fast forward to predict its fate, but we can also rewind it to recreate its origin. So Dr. Weinberg introduced Friedman's critical density and wrote some ideas about the universe's fate. And I'm not going to talk too much about that because we have modern information now, that pretty recent theories that we don't really need to go into that, because those recent theories sort of push us in a direction of what the fate of the universe is going to be. But if you hit the rewind button hard and long enough, almost all the way back to the beginning of time, you can see that all things must have been a lot closer together than they are now. Okay, so what is the implications of those implications? So when I talk about closer, I mean a lot closer. No, when I talk about those things, I mean really, 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 really close. Not normal close, weirdly close. Like particle physics is close. Like how close things are in particle physics. And from an infinitesimal and hypothetical point before particle physics close is when maybe it all started. We now call that the origin of how the universe progressed from that point, the Big Bang. All right, so that was Hubble's contribution to the Big Bang. Here is the CMB, the cosmic microwave background. This comes from Dr. Weinberg's third chapter, the cosmic microwave background. And if you know this story at all, it might have been presented to you in, these guys happened to discover this thing. It's not exactly how it happened. I'm going to have to read this off of this because it's too small on my screen to read here. Did you know that theoretical physicists actually predicted the cosmic microwave background over 10 years before its discovery? It was postulated from exploring the particle physics of the early universe. However, they did not predict its importance as corroborating evidence of the Big Bang theory. So its actual experimental verification lagged its actual discovery. So the cosmic microwave background didn't just drop out of the ether. It was an impending discovery, so to speak, predicted by theoretical physics. So these two gentlemen here are credited with the discovery of the cosmic microwave background. In 1964, Arno Penzias and Robert Wilson worked for Bell Labs in Holmdel, New Jersey. They were commissioning a radio telescope for a survey of the Milky Way. They were troubleshooting sources of noise in the signal from the receiving system. So they had set up this radio astronomy device and were about to measure the Milky Way. They had nothing to do with the cosmic microwave background or the Big Bang. They were troubleshooting sources of noise in that setup, and they were measuring to find those spurious sources of noise so they could eliminate them in the wavelength of 7.35 centimeters. They found a stubborn source of noise there that they could not figure out what it was and could not eliminate. That source of noise didn't depend upon anything like the time of day or the direction of where they pointed the equipment. And if you hear that it doesn't depend upon the direction that they were pointing the equipment, and you remember what we were just talking about the universe being homogeneous and isotropic, and connect those two things, then you are correct. The signal corresponds to the excitation of electrons in a closed thermal system, and that's called being in a black body. Is referred to as a black body temperature, and it corresponded to about 3.5 K, which means about 3.5 degrees above absolute zero. Through colleagues, Penzias and Wilson were put into contact with physicists of Princeton who had theories about the leftover radiation of the early universe and were setting up at the time their own experiments. The theoretical physicists there were Peebles and Dick, and the experimental physicists, I believe, were Roll and Wilkinson. Penzias and Wilson had, before they, the Princeton people, had finished setting up and doing any measurements, Penzias and Wilson had found this theorized leftover radiation. They determined that after talking. They wrote different papers, Penzias and Wilson about the discovery, and Peebles and others about the theoretical physics behind it. And Penzias and Wilson ended up winning the 1978 Nobel Prize in Physics for their discovery. That is a Wilson, who looks like Opie's father here, and that's Penzias right there. So what is the CMB then? I mean, what caused it? What is it? After the Big Bang, the expanding of universe was very hot and very dense. A sort of a soup of radiation and elementary particles. Matter in no way, shape, or form existed the way it does now. Even though the universe was expanding rapidly, the mean free time between radiation particle interactions was imaginably fast. The way I thought to maybe describe this to you is the difference between jogging in an empty field and maybe jogging in Grand Central Station at peak rush hour. So Grand Central Station at peak rush hour was the early universe. The radiation particles were in what's called thermal equilibrium. That's that black body thing we talked about, and and behaved like a black body. The universe cooled in the thermal equilibrium until it reached about 3000 K, 3000 degrees above zero. Then the electrons bound to atomic nuclei, so the regular matter formed at 3000 K. And once those electrons were pulled in and regular matter was formed, the light that was pinging around in that very dense state was released. The universe's density dropped, the radiation was released, and the universe continues to expand. That light that was now released expanded with the rest of the universe, so the wavelengths got longer. If the wavelengths got longer, then it redshifted to the cooler red light, and that redshifted light, that black body radiation we see now, and the modern estimate of that temperature of that redshifted light is 2.725 degrees K, and that is the cosmic microwave background. It's actually direct evidence predicted by theoretical physicists before it was discovered of the Big Bang. Why do I keep saying black body and stress the thermal equilibrium portion of this? Well, if you remember that red shift, blue shift, where we had that pattern that we recognized as this particular compound, and we see in red shifted light the same pattern, but it has different numbers. It shifted to the left, or it shifted to the right, but we recognize that pattern. Scientists wanted to make sure that this was actually the cosmic microwave background they found. They wanted to make sure they recognized that it maintained the same pattern. And that's very important. What they ended up doing is seeing this here pattern, this curve, that indicates, this is called a Planck distribution. This is the Planck distribution of the cosmic microwave background. So they predicted, they wanted to see that if what Wilson and Penzias found is the cosmic microwave background, it should still have the property of being a radiation from a black body. And that's what all the satellites we've set up and all the observations of the cosmic microwave background wanted to achieve, is measuring points along this curve here to see whether or not it fit the characteristic curve of a black body, this Planck distribution. And you can see the dots here of different colors. These are actual measurements, and it fits very well to the curve, doesn't it? Right along that curve. So this CMB actually is from a black body. It is the cooled radiation from the early universe. Poetically, but almost literally, the CMB is the smoking gun of the Big Bang. Oh, and I had to search 100 curves, I think, before I came across this one. You see that this curve here is plotted on a logarithmic scale, and I had to do some quick basic physics calculations, but I think right here at 4.3 gigahertz, it corresponds to, right about here, corresponds to, maybe this point here, corresponds to Wilson's and Penzias's original discovery. They were a little off in temperature, though, so they're probably either above or below the curve there. So, but I had to, because they missed the peak by quite a bit, right? So I had to find this curve so I could show you about where the original discovery was on the curve. And that's a picture of one of the of our our total knowledge of and some of our current research on the cosmic microwave background. Some of our current research has to do with this statistical variation in the temperature of the CMB throughout the universe, and it doesn't vary very much at all, but the size of these variations is very important, and I will explain that again on the last slide. So in another chapter, which I thought was very interesting, Dr. Weinberg described some of the ticks of the clock in the early universe. Now, you want to listen to, say, how things were and get a general idea of how things were at these ticks. Some of these numbers might be a little off due to the fact that this stuff was taken 40 years. The original material was, oh gosh, almost 50 years ago, 45 years ago. So we begin on our first frame, lights up. We start somewhere very soon after the Big Bang. The temperature is about 100 billion degrees. The universe is a soup of matter and radiation and is in a state of thermal equilibrium. The only matter exists at this point is the electron, the positron, the neutrinos and antineutrinos, and the photon. That's it. Remember that free energy we talked about? Well, they can't exist. Those things just immediately get blown apart in this soup. The density of the universe is approximately 3.8 billion times of liquid water. Now we have to, this is energy density we're talking about at this point, because regular matter doesn't exist yet, but still 3.8 billion times of liquid water. So when I said really, really, really close, that's how close we were. That's how dense the universe was. So 0.11 seconds after that first frame that we just talked about, the temperature has cooled to a mere 30 billion degrees. The universe is still a soup of matter and radiation and is in a state of thermal equilibrium. The only matter that exists now is the electron and the positron, the neutrinos and antineutrinos and the photon. But free neutrons and protons are beginning to form, and they are being blasted apart. The ratios start differentiating. Neutrons are a lot less stable than protons. So the neutron density goes down, it's 38%, and the proton density is about 62%. The density of the universe is approximately 30 billion instead of 30 million times of liquid water instead of 3.8 billion. The next tick of the clock is almost a little bit more than 1 second after the beginning of the universe. The temperature is 10 billion degrees K. The universe is a soup of matter and radiation, and it is a state of thermal equilibrium. The universe now, though, becomes transparent to neutrinos. So neutrinos fall out of the and antineutrinos fall out of the soup. The microwave, they are now traveling through space freely. The universe becomes free neutrons and protons are formed and blasted out of existence. The ratios of neutrons and protons are now 24 to 76%, and the density of the universe is now only 380,000 times that of liquid water. Another tick, almost 14 seconds have elapsed. The temperature is only 3 billion degrees K. Electrons and positrons are now stable at this temperature, and they begin to annihilate each other. Neutrinos, remember, antimatter and matter don't play well together. If they see each other, they'll annihilate each other. Neutrinos previously freed are now cooler than the rest of the universe. The rest of the universe is still going through this these nuclear reactions. The neutrinos are no longer participating. The balance of neutrons to protons is now 17 to 83%, and some stable nuclei, that's the protons and neutrons together, now can form. Helium and atomic weights above that are still suppressed due to nuclear reaction reasons. Basically, deuterium is the bottleneck there. 3 minutes, 2 seconds have now elapsed at our next tick. The temperature is 1 billion degrees K, so it's really starting to get chilly. Electrons and positrons are mostly gone. They've annihilated most of each other. The universe is now mostly consists of photons, neutrinos, and antineutrinos. The balance of neutrons to protons is 14% to 86%, and some stable nuclei can form. However, the helium nuclei can form, but are still suppressed because of that deuterium bottleneck. Still not stable. A brief intermission there, some little bit of time after there, approximately 3 minutes and 46 seconds have passed. Deuterium nuclei are now stable, and so helium nuclei can now form at a rate twice that of the available neutrons in the universe. So about 13% neutrons to 80% protons gives us about a helium formation rate where hydrogen is going to be the balance, and the neutron-driven helium is 26%. The temperature there is about 900 million K, so getting quite cold. The next tick, 34 minutes and 40 seconds have elapsed, so real long stretch of time now. The temperature is 300 million K. Electrons and positrons are gone, except for 1 part in 100 million. Those are the surviving electrons. Nuclear processes have now stopped. The temperature here, this cool temperature of only 300 million degrees K, means the nuclear processes have stopped. Nuclear particles are bound in mostly hydrogen or helium nuclei at this point, and is still too hot to form stable atoms. And the density of the universe, we've gone to millions above the density of billions or millions above the density of water. We're now under the density of water by not to about 1/10 that of water on Earth. So where does this play end? Well, the lights fade on not much interesting happened after that point until 700,000 years later. This is one specifically that we will come back to, that figure. The temperature drops now below 3,000 degrees K, and stable atoms are now possible. The free electrons now get grabbed by the nuclei that are floating around and pair up, and they start making happy little atoms. The universe becomes transparent to radiation. What happened there? Well, we get the light is released, and we get the cosmic microwave background. Stars and galaxies begin to form, and then the universe continues happily expanding beyond that, and nothing else interesting happens really until Dr. Weinberg writes this book, the first 3 minutes. So, Finn. So, afterthoughts. That's the Big Bang Theory. So, things that we should think about on that Big Bang Theory. So, you saw, we talked about the cosmic microwave background, and you saw that that light got released, and we can measure it now. We talked about before that microwave, before that light radiation was released, that before that happened, in that those ticks of the clock, I did mention that the neutrinos were released before that. So therefore, there should be a cosmic neutrino background. And as predicted, they did find the cosmic neutrino background, and they estimated it about 2 degrees K, and they actually measure it at about 1.75 degrees K. Cosmic inflation in the CMB. I talked about the size of the variations in the cosmic microwave background. Well, they're bigger than they should be. And the problem with them being bigger than they should be is that the only way that could have happened at the time that the cosmic microwave background was released, the only way that could have happened that those grains, those variations be as big as not the number up and down, but the width of those variations that can only be that size, is if the universe expanded at that time faster than the speed of light. Now remember that yellow, italic, and bold, that through was a very important word in the description that the speed of light is an absolute fastest thing that you can ever travel through space. But this is space expanding itself. Space isn't traveling through space. Space is expanding itself, and that's why this inflationary period, this cosmic inflation, can happen faster than the speed of light. Dr. Weinberg talked about not thinking too much about the Big Bang, what was happening before it, because not only is it very difficult to predict what was happening, even though people do, he himself and others have theorized and play with the particle physics about stuff that happened before that. Going all the way back to trying to predict it, time itself and the physics that we understand today, even the hairy minded theory of particle physics, just break down once things get small, hot, and dense enough. That it's very difficult to theorize about that when some of those things just even boggle the mind that they could possibly exist. That's not to say that somebody isn't going to come up with a brilliant theory at some point, but after a certain point, going all the way back to the beginning might just be an impossible task. And whether that even exists or not, whether it even makes sense that there was something there before time. Dark matter and dark energy. Dr. Weinberg did talk about dark matter in his afterwards, the updated version of the book. So he was aware of that. He did not talk about dark energy, though. And if everyone remembers dark matter, we noticed that the galaxies are spinning faster than they could. So there must be some sort of matter in those galaxies that we can't, holding the galaxies together against that spin, and we call that stuff dark matter. We don't know what it is. And dark energy has this effect on the speed that things are flying apart in the universe. Very distant objects are flying apart in the universe. And we don't know what that is either, and we call that dark energy. And finally, this dark energy and this speeding up things flying apart in the universe makes this fate of the universe maybe the preferred theory at this point, the heat death of the universe. And that's when things are far enough apart and the stars have all run out of fuel, and the heat just slowly gets distributed over these huge spaces that basically nothing can happen anymore in the universe. That's a long. You talk about billions of years, thinking that's a long time, the age of the universe. We're talking about trillions of years now. So, long time. And this last slide is our current thoughts on the Big Bang. Here's this thing called quantum fluctuations that we're not supposed to really think that too much about. Here's the cosmic inflation, where the universe expanded faster than the speed of light. Here we have the releasing of the light, but instead of that 700,000 time frame, we're now about half of that. The releasing of the light in the cosmic microwave background that is now cooled to around 3 degrees K. And before matter formed, when the stars and matter formed, and then there's this long billions of years of expansion, and then you know, in here it looks like it's starting to curve, and that curve is due to dark energy and accelerated expansion. And here's the Big Bang expansion of about 13.77 billion years. And that is my presentation on Dr. Weinberg's work of the first 3 minutes. And I urge everyone here to enjoy, think about joining an astronomy club. And stay safe tonight, everyone, and enjoy your evening.
All right. Thank you, Paul. Let me move this back out here. All right. So normally I would come out to you guys when we're doing the Q&A. I'm going to try and social distance. So what I'm going to do is anyone who has a question, you're going to come up to the mic, okay? That being said, we are doing a Q&A. Thank you, Paul, for another great presentation.
Thank you.
A couple safety reminders for everyone here, because I do believe some people came in after my first safety briefing. If you need to use the bathroom, we have the porta potty to my right, your left. We do have a gift shop and little museum area open, and I will be in there after Q&A to help you out if you need any help with that. Each of those different sheds does house a telescope. Chances are there are volunteers at least 1 or 2 of them, and you can ask them questions. Do please follow their instructions. As always, when we go to leave, we are using headlights because we do not like getting run over. No one likes getting run over. That being said, any flashlights, we are keeping them pointed towards the ground. We do not need to needlessly blind anyone and wreck night vision as much as possible. And also, we are in a state park. Please, when we have trash, we take it with us. That way we keep the state park nice. We're going to start off with one of the first questions from our online one. And the first question I had, did they ever turn the particle accelerator at CERN back on like they said they were going to do?
Unless, I mean, there was a shutdown due to a break and recalibration a while ago, and then they had turned it on since. But I don't know whether or not whether there is anything recent that I'm aware of. I know that they do shut it down and then do planned upgrades, but that's all part of a schedule and has nothing to do with you know, misfirings of the particle accelerator. So if it is currently shut down, I believe it's probably due to some planned out upgrade.
All right. Was there a question with our audience here? You can come up if you have a question. Don't be shy. Does anyone have a question? All right. Well, I'm waiting for someone to come up with a question over there. Our next question was actually more of a snarky comment. So, is that? I believe you were talking about why particles can't go through lead, and so someone commented, "Is that why Superman can't see through lead?" And I believe I actually replied, "I thought he could just melt the lead with the laser vision."
Neutrinos are actually a very tricky subject, and actually relatively recently we've been able to capture them. If you at all familiar with neutrinos, most of the detectors are built in mines way below the surface of the Earth. They are huge pools of water, and they occasionally, over months period of time, they'll get a flash in that pool from a neutrino hitting it, and billions and billions of neutrinos go through that pool in the Earth on a second-by-second basis. So neutrinos really don't want to react with normal matter. So that is why that lead would not react with neutrinos. Neutrinos are just very squirrely.
All right. Question from out here. You can feel free to come up and use the mic so our people online can also hear it.
Can they trace back to the point of the Big Bang?
They, of course, I said that we shouldn't think about it too much, but of course they do. And they theorize as far back as they could, but literally the physics no longer makes sense once you reach a certain point. So you can't go all the way back to zero. Time itself no longer makes sense in those contexts. If you reach a certain point called the Planck distance, physics breaks down. They think that it's possible even that space itself is a quantum property, and so it doesn't make sense to break things down so small that physics no longer makes sense.
But is there a general direction in the sky
that the Big Bang happened?
Right.
So it is not the way I've heard it described, it's not an explosion the way we would think of as an explosion. And physicists have long gnashed their teeth at people calling the Big Bang theory the Big Bang, because it suggests to people that it was an explosion. But what's really happened is if you and I were to hold a rubber sheet between us, and then we were to step back and then start stretching that rubber sheet, and all the matter in the universe are dots on that sheet, that's what's actually happening, is that rubber sheet space is stretching or spreading or expanding, and it was never actually an explosion boom in the sense that it was this very energetic event. So does it actually have an origin point like that? Well, all points were contained in that thing. So it was, it doesn't have an origin point that we can point to in space.
All right. Our online audience actually had a bounce-off question that I think you had started covering. Was, do we know where the center of the universe is, and do we know how far we are from it?
Yeah, again, that's exactly the same. That all points are spreading equally from each other, so that we being in space, we can't point to an actual origin, because no matter where you are in the universe is expanding equally. That's that isotropic and homogeneous thing. No matter where you are in the universe, everything is expanding away according to Hubble's law, and so there is no point that's just sitting there that was the point of origin. Everything is expanding away from everything else.
Also, I want to thank you for that question, because that led perfectly into that online question. All right. You said you had another question, sir, or?
Well, considering that the universe is still expanding, does that mean that the Big Bang is still happening to this very moment?
The effects. It was a very energetic event, and those effects will be felt throughout the universe for all of time.
Thank you.
You're welcome.
All right, Paul. I do have a couple last-minute questions for the online from the online crowd. Does that expansion mean that if we were to try to travel to a distant star or galaxy, we would also have to factor in the fact that things are in fact running away from us?
Very much so. Over not even galactic distances, but further distances. If we were to calculate some sort of trajectory to go there, there are some things, depending upon the speed you are traveling, that you could just not get to because it's traveling away from us too fast. In fact, the universe itself has a limit called the observable universe, and light at extreme distances can't even travel fast enough. So there are portions of the universe. In fact, the universe itself might be infinite. We don't know, but there are most likely beyond that limit of the observable universe that might exist. We would just, it's not that we don't have the technology or will ever be able to develop the technology. It's that we are prohibited by the physics, because we can't travel faster than light, from ever reaching or observing that portion of the universe.
All right, last couple questions. Why did the CMB picture look like it was a weird world map?
Yeah, I wondered that myself, and I don't know the particular answer to that, but it might just happen to be the projection that they chose to use. And remember that 3D objects don't project very well without being stretched to 2D surfaces like a screen or on paper, and so it just is probably the projection that the science team chose to use for that particular representation of a 3D object.
Here's a unit-based question. You said 3.8 billion times water. What? Was there a unit supposed to be attached there, or was there a reference? Like, is it 3.8 billion times the water on Earth?
It is the water on Earth, and it's the density of water. So the density of water, if I remember correctly, is 1 cubic centimeter equals 1 gram. So that is that's the density of water on Earth.
Okay, so it was 3.8 billion times the water on Earth.
Yep.
I was also wondering that, because you didn't say on Earth. It was 1.83 billion times the water. I'm like, anyhow, the next question actually related to presentations. Will they show any live pictures of the sky tonight? And the answer is unfortunately no. I did answer this in chat, but I figured I'd take a minute just to say we currently don't have the necessary equipment to do that in a way that would be pleasing to viewers, as well as not painful to the people doing it. We have discussed it, and there are ways to do it. Like I said, we just currently don't have that technology here. It might come later with a different sort of presentation. I can't rule it out, but as of right now, that is not something we can do. But who knows, if someone wants to back a project like that, and if you want to come up and help set it up, we could probably make something like that happen in the future. All right. So one last follow-up question was, so due to the elasticity that you described with everything expanding, do we know if it will reverse and collapse again, like you stretch a rubber band too far and eventually it goes, yeah, no?
Yeah, that's the critical density that I talked about, and the possible fates of the universe that dark energy seems to be overriding for us at the moment. So before dark energy was theorized, and careful observations have determined that distant galaxies are actually accelerating away from us. There were 3 possible fates of the universe. One was a bounce, one was a steady state, and then one was an elliptical or an increasing an escape velocity, a type of scenario. So the bounce would be that gravity would eventually overcome all the galaxies, motion away from each other. There was a neutral where a straight line relationship existed, where we were in balance with the gravity, and we would travel at a slow rate away from us. But we found out that a steady rate away from us. The dark energy that we now believe is the correct answer, that something is pushing the galaxies faster and faster away from each other, override those 3 scenarios, and that is the current theory, that this dark energy is just pushing distant galaxies away from us faster and faster and faster.
That also brought up another question. So if things were to collapse, do we have an estimate how long before that happens? And if the collapse occurred, would we have any idea at all what will occur with all of the matter that currently exists?
Dr. Weinberg did speak about this, because dark energy did not. And of course, if we were to start getting back into densities where things were so close together that photons were heating things up again, we would of course not exist anymore. Matter would start, as we know it, would start not to exist anymore, and things would just get hotter and hotter, and matter would be at some point completely annihilated, or exist in, again, thermal equilibrium with the available energy. So it wouldn't be good news for any people who happen to be around at that time. As far as when, it all depends upon that critical density, but our actual observations now is that that's not what is happening. So we can't measure that critical density, because we've in fact observed that that density doesn't exist, because things are moving away from each other faster and faster. So every that acceleration, every time you measure a speed, you get a critical density, but now things are moving faster, so now there's a new critical density. So the quick answer to that is that that critical density ceases to exist because things are accelerating away from each other.
All right. Thank you, Paul. Thank you for everyone who came out and listened to us. And thank you to our online viewers. If you have any additional questions, you can always add them in the YouTube comments on the video. That's going to probably show up a couple minutes after we end stream. And as always, have a good night.
Good night, everyone.